Right, so Rachel Rosen is an associate professor at Carnegie Mellon University, where she works at the intersection of gravity and quantum field theory. She improves our understanding of gravity using the methodology of particle physics. She was previously at Columbia and did a postdoc at the Oscar Klein Center in Stockholm, and she's answering the question, the big question: what is quantum gravity?
Okay, thanks very much, and thanks especially to the organizers. I've really enjoyed my day-to-day talking to people here, and also the opportunity to talk about these fun ideas. So yes, my task is to answer the question, what is quantum gravity? In some sense, this is an unanswerable question. But what I want you to walk away with from today is that the notion that quantum gravity is what happens when we try and get particle physics to talk to general relativity, to talk to the theory of gravity. Now, there's this sort of standard lore that particle physics and gravity are fundamentally incompatible with each other, that as soon as you take quantum mechanics and you try and combine it with gravity, things go horribly awry. And that's not true. That's simply not true. And so, in fact, another one of the takeaway messages from today is that I want to convince people that, in fact, the standard theory of gravity, general relativity, already has baked within it a perfectly good quantum field theory of gravity. And that there's no fundamental incompatibility there. Nevertheless, it's not true that we totally understand quantum gravity. And in fact, many of the fundamental mysteries in high energy theory and particle physics today are precisely at this intersection between particle physics and gravity. So after first convincing you that there's nothing wrong, I'm then going to tell you what these outstanding problems still are. All right, so first we're going to talk about gravity and particle physics, then what the issues are. I hope to touch very briefly on some current developments. And then I thought it was a nice suggestion as well, and Grant touched on this earlier, to talk about some kinds of pathways for doing this type of research if you have students who are interested. Use the clicker. Okay, very good. So gravity meets particle physics. So this is the standard model of elementary particles. I believe we saw it earlier today in Nick's talk. I just pulled this from Wikipedia. So these are all of the known fundamental particles. You have your matter particles and the quarks and leptons. So these are our spin half particles. You have the most recent addition. This is the spin 0 Higgs boson. And then you have these four guys here, the gauge bosons, which are spin 1 particles. So the gauge bosons are the mediators of forces. They're the things that convey the forces between the matter particles. So the particle responsible for conveying the strong force is this gluon, a massless particle. The photon conveys the electromagnetic force, also a massless spin 1 particle. And then we have the W and Z bosons, which are responsible for conveying the weak force. So these are charged, massive, also spin 1 bosons. Now, you probably know that there are four fundamental forces in nature. There's the strong force, there's the electromagnetic force, there's the weak force, and there's also gravity. And you might notice that there's no gauge boson in the standard model of particle physics associated with the gravitational force. And so it would be very natural to ask, what about gravity? Why isn't this included in the standard model of particle physics? So traditionally, we think about gravity very, very differently than we think about the other three forces. So the theory of gravity that we use today is the theory of general relativity. This dates back to 1915. And as the story goes, in fact, you don't even have to think of gravity as a force at all. You could think of it in terms of space-time curvature instead. All right, so in gravity, the fundamental object here is this metric, g mu nu. This is what tells you about the distances between points in your space-time. This is what encodes the curvature. And the thing that tells you how your space-time curves, and in particular, as the story goes, space-time should curve in response to matter, and then particles follow trajectories in this curved space-time. And so what tells you how your space-time curves in response to matter is Einstein's equations here. So even if you've never seen this before, you should read the right-hand side as your input. So this g is nothing other than Newton's constant, but this t mu nu is where you input what the matter or energy is that's going to bend your space-time. And then the output is the left-hand side of this equation here, which tells you how your space-time is curved. So these pieces here contain second derivatives of this metric here. All right, and you can think of this as being the relativistic generalization of the gravitational Poisson equation. So in fact, this is exactly what this is. So this is our usual gravitational equation that we're familiar with from Newtonian gravity. On the right-hand side, we have some matter density, and on the left-hand side, we have two derivatives of the gravitational potential. And in fact, you could start from this equation here, and you can ask, how can I make Newtonian gravity compatible with special relativity? And you would be generically led from this equation here to updating it into this equation here. In fact, this is more or less the path that Einstein took in originally writing down these equations. So you can think of Einstein's equations as being due to wanting to make Newtonian gravity compatible with special relativity. Okay. So why is gravity so different? Why can we talk about gravity in terms of the curvature of space-time as opposed to being a force mediated by a particle? One way that you can see this is to perform a very simple thought experiment. You can imagine taking some small mass, so some little blob of mass m, and putting it in a uniform gravitational field that points downwards. And then if we just want to know the acceleration of that particle due to the gravitational field, you can plug it in to Newton's second law. The m's are going to exactly cancel. And what that means is that the acceleration of each particle is due only to the strength of the gravitational field and is completely independent of the mass of the particle itself. So in some sense, you should think of this as being very non-trivial, that these two m's cancel. So the m on the left-hand side is the mass associated with the inertia of the particle. The mass on the right-hand side, you could think of as being almost like the charge of the particle under the gravitational force. And a priori, there's no reason why these two masses should be the same as each other. Nevertheless, they are, so they cancel identically. This is known as the equivalence principle, and so that the acceleration is the same for all particles. And what this means is that if you want to talk about particles moving through some space-time geometry, and that geometry being responsible for their acceleration, this is telling you that all particles are going to see the same geometry. So because all particles accelerate in the same way, they're all following the same path, and you can talk about one space-time geometry that all of your particles are moving through. So you can say, okay, why couldn't I do the same thing for electromagnetism? So there the analog would be, we're going to put some charged particle now in a constant electromagnetic field and run the same exercise. So we stick this in to Newton's second law, we calculate the acceleration, and now what we see is that the acceleration actually depends on properties of the particle itself. So the acceleration of the particle is going to depend on what that charge of the particle is and what the mass is. And so the different particles are going to see different space-time geometries. If you want to associate the movement of the particle to a given space-time geometry, there isn't one geometry that you can describe. And so this geometric nature of the force really wouldn't work for a theory like electromagnetism. So gravity is truly special in this regard. All right, so the theory of gravity that we've been talking about is general relativity. This is a purely classical theory. So when you're thinking about gravity as being the curvature of space-time, everything that you're talking about is classical physics. And you could ask, well, maybe that's the end of the story. Maybe gravity is just truly different. We have the standard model of particle physics. It has the 4 gauge bosons. Well, all right, plus or minus. Anyway, you have the 3 types of gauge bosons responsible for mediating the strong force, the weak force, and the electromagnetic force. And maybe we shouldn't even think of gravity as a force at all. Maybe it doesn't belong as part of the standard model. Maybe it's just space-time curvature. You can't do that. That's not consistent. And the reason for that is precisely, you can think of, because of Einstein's equations. So notice that on the right-hand side here, the input is the matter of your universe. And we know that at the end of the day, matter itself is quantized. And there's no way of just quantizing the right-hand side of this equation without talking about how to quantize the left-hand side of this equation too. So it's simply inconsistent to have a universe in which your matter is quantized, but gravity is purely classical. All right, so then the question that we're left with is that if we want to construct a quantum theory of gravity, what should this look like? And so in order to try and answer this question, I'm actually going to throw out everything that I just told you about general relativity and about the geometric nature of gravity and how beautiful it is that we can describe gravity not at all in terms of a force. And I'm going to start completely from scratch. And I'm going to say, okay, let's pretend that we're a particle physicist. We've just discovered that massive bodies can attract each other. What theory are we going to write down as a particle physicist to describe this force? So what boson should we introduce, or what particle should we introduce to describe this? All right, so as we actually just heard earlier, we know that forces are mediated by bosons and not by fermions. This has to do with conservation of angular momentum. And so we need our force-carrying particle to be a particle with integer spin. So here I've drawn a little Feynman diagram, but you can really just think of this as I have two masses, M1 and M2. They're going to be attracted to each other gravitationally, and the way that they know to be attracted to each other is that they're exchanging this graviton here, and this graviton is going to be a particle that has some mass and some spin. All right, so already off the bat, we're saying we have to restrict our attention to bosons if we want this to be a particle that mediates a force. All right, so if we're good particle physicists, we should start with the simplest possibility first and look at a spin zero particle, like so. And it turns out that if you wanted to describe a force of gravity mediated by a spin zero particle, you get exactly the correct Newtonian force law for doing that. So phenomenologically, this all seems great. You might think, okay, I'm done. That was super easy. I have a spin zero graviton. That's the end of the day. It turns out, though, that a force of gravity that's mediated by a spin zero boson doesn't give you any bending of light by the sun. So this was a very important prediction of general relativity that was confirmed experimentally. And if you had this spin zero graviton, you would not agree with this prediction. So while there's nothing wrong with this from a theoretical point of view, we know we can rule it out phenomenologically. All right, on to the next boson. Let's try spin one instead. Now here you can use your intuition from electromagnetism. We know in electromagnetism that like charges repel each other. And the same would be true if you had a spin one graviton. You would find that two positive masses would repel each other rather than being attracted to each other. So also immediately, on phenomenological grounds, you can rule out the possibility of a spin one graviton. All right, let me skip spin two for a second. And note that for massless high spin particles, so for particles of spin 3 or greater, there are actually no-go theorems, and this is due to Weinberg in the 60s, that forbid interacting theories of massless high-spin particles. So basically, we already know just based on theoretical grounds now that we can't have a particle of spin 3 or higher mediating our gravitational force. That's a no-go. And so what that means is that we're left with a spin 2 particle if we want to describe the gravitational force. All right, and I've kind of glossed over the fact that I'm only interested in massless particles here, but we pick them to be massless to appropriately get the long-range force of gravity. Ask me more about this if you're interested. All right, very good. So in fact, in 1939, Fierz and Pauli, they constructed the wave equations for a free massless spin 2 particle. So this is a spin 2 particle without any self-interactions or without talking to anything else. They just wrote down what the wave equations for that particle would look like. And in the same paper, they took Einstein's equations and they expanded them to first order in the metric perturbation. So what that means is that they took this full metric g mu nu, they wrote it in terms of a flat space-time metric eta mu nu, plus some perturbation h mu nu, and they only kept the leading order pieces. And what they showed is that these two equations were identical to each other. So in other words, general relativity already contains in it the same equation as the wave equation for a free massless spin 2 particle. Now, apparently, even at that point, people were still skeptical that these two theories should have anything to do with each other. So this is how ingrained it was that people thought that the theory of gravity was purely geometric and had nothing to do with particle physics. Even showing that these two theories were effectively the same at leading order, people were sort of like, yeah, I don't know, let's see. All right, but it turns out they were wrong. And in fact, starting with work of Weinberg in the 1960s, people have been able to show that general relativity is the unique Lorentz invariant low energy theory of an interacting massless spin 2 particle. So on the previous slide, we were talking about just a free spin 2 particle with no self-interactions. If you want the particle to have self-interactions, which it needs to for consistency in order to be our graviton, it turns out that there's only one theory that you can write down, and that's the theory of general relativity. So even if Einstein had never come along and written down this elegant and geometric theory of gravity, it would have been discovered by particle physicists in the 60s and 70s, the exact same theory. And you would end up with these equations again. All right, so I return to my original question, which is, why isn't there a graviton in the standard model of elementary particle physics? Certainly at this level, it doesn't seem out of place that we might look at a slightly beyond the standard model of elementary particles and add to it this particle that mediates the gravitational force, which would be a massless, no charge, and spin 2 particle. All right, so again, to summarize, the point that I want to make is that in fact, general relativity already contained in it a theory of particle physics, and in particular, a theory of quantum field theory. Sorry, a quantum field theory. And in fact, you didn't even have to change general relativity at all to get this quantum field theory out of it. All right, so what's the problem? Why do people care so much about quantum gravity? So it turns out that when you look at physics at the intersection of gravity and particle physics, you inevitably run into what I think are 3 of the most pressing problems of fundamental physics today. So the first of these that I'm going to talk about is the problem of UV completion, and I'll say more about what that means. The second of these problems is the black hole information problem, which I'm sure you guys have heard about before popularly. The third is the cosmological constant problem, which Grant also alluded to this morning, but I'll say more in detail about the cosmological constant problem as well. Are there any questions? I'm happy to be interrupted. Okay. All right. So the UV complete problem is the fact that, so what we said earlier is that general relativity is the unique low energy theory of an interacting massless spin 2 particle. And the emphasis now should be on the fact that we had to say the words low energy when we said this. What that means is that in reality, general relativity is actually a theory that's only valid at certain large distances or certain low energies. And I'll talk in a minute about what that particular scale is. But as a theory, it contains in some sense the seeds of its own destruction. And we know that if we try and push it up to higher energies or to shorter distances, the theory stops being predictive. We stop being able to use it to make predictions about how gravity should behave. And so the theory of gravity by itself, the theory of general relativity, I should say, is actually incomplete. We know that it's incomplete. It can't be the full story. All right, so just to make an analogy with what I'm talking about, you can think of the theory of general relativity in some sense like a theory of hydrodynamics or a theory of fluid dynamics. It's a perfectly good way of describing a system at a certain scale. So in particular, if I'm at certain large distances, compared to the size of my water molecule, compared to an angstrom, I have a nice set of equations that I can use to describe my hydrodynamics. Nevertheless, those equations don't tell me anything about the microscopic properties of that theory. And in fact, there can be multiple microscopic theories that all give me the same macroscopic theory, that give me the same fluid equations at the end of the day. And just knowing those equations doesn't tell me what the microscopic theory is. So we know, for example, that if we're talking about water, that if we go to short enough distances, it's described by this molecular theory, but we have to use an entirely new language to describe the physics that we're talking about. And that there's really no way of extrapolating from the long distance or low energy physics up to the short distance or high energy physics. So in this case, you should think of general relativity as being like this long distance or low energy theory. It's a perfectly valid theory for a certain energy scale, but once you go beyond that energy scale, we can't extrapolate it to figure out what the shortest distance physics can be. All right, so I'm using these words low energy somewhat loosely. In fact, what I mean by low energy is an incredibly high energy scale. So we heard about GeV earlier, but this cutoff scale where general relativity breaks down is known as the Planck scale. In units of kilograms, it's 10 to the minus 8 kilograms. In units of GeV, it's 10 to the 19 GeV. So compare that with the mass of a proton, which is 1 GeV. So this is a gigantic scale for a theory of fundamental physics. I put this picture of a fruit fly here because I think this is approximately the weight of a fruit fly. So this might seem, you might say, oh, but that's pretty light. That's a pretty small energy scale. But imagine taking the mass of a fruit fly and applying E equals mc squared, converting all of that to energy, and giving all of that energy to one fundamental particle. That would be a huge amount of energy for a single fundamental particle. But that's the energy scales at which general relativity is breaking down. Said equivalently, so if you had a particle at this energy scale, it could probe physics at a distance given by this Planck length, L Planck, which is at the order of 10 to the minus 35 meters. So again, this is an incredibly short distance at which general relativity breaks down, which means that there's more or less no experiment that we can build or that we can ever hope of building that's going to probe these energy scales here. So it's truly mysterious, and we don't have a lot of hope or a lot of help coming from experimental observation. All right, now over the years, there have been many proposed solutions. String theory is perhaps the most famous of these, and there's a large program now that seems to be landing on the fact that if you want a weakly coupled UV completion, so we talk about UV in terms of ultraviolet or high energy, so if you want a weakly coupled completion of general relativity, it's looking more and more like string theory is going to be the unique weakly coupled UV completion. However, I think a fairly large loophole in these arguments is that you could have UV completions that are strongly coupled. So basically, when we say that a UV completion is weakly coupled, what that means is that we can introduce new degrees of freedom into our theory that are weakly coupled, which allows us to calculate things perturbatively. Nevertheless, it doesn't have to be the case what's the right way of saying it? That the UV completion of gravity is something that we can understand perturbatively. But then we're really up a tree because we don't have any good handle on how to calculate things or how to learn anything new. And then there are dots down here because this is a really vast oversimplification of the proposed solutions. But I just wanted to highlight these two things. All right, the second very important problem at the intersection of particle physics and gravity is a black hole information problem. So if you just take general relativity and you don't say anything, you don't add any quantum mechanics to it, you would say that a black hole is a stable object. So in fact, famously, people say the black hole is so dense that not even light can escape. You don't expect anything to come out of your black hole, and therefore you expect it just to remain how it is for all time. But it turns out that if you treat your theory quantum mechanically, and by this I mean something very specific, so this calculation is done in what's known as the semi-classical approximation. So you treat your black hole as a classical background, so you have some classical space-time geometry, and then you put quantum fields in this classical background. So it's sort of a hybrid mixture of classical and quantum. Nevertheless, this is a perfectly valid regime, approximate regime to work in. So if you work in this semi-classical regime, what Hawking showed in the 1970s is in fact that black holes should radiate, and they should radiate with some temperature T. Now, black holes famously can be characterized entirely by very simple numbers. So in particular, if you specify a black hole's mass, its charge, and its spin, you've entirely specified everything there is to know about that black hole. It doesn't matter how it was formed. It doesn't matter what went into it. All black holes with the same mass, charge, and spin are absolutely identical to one another. So what that means is that when this black hole radiates away, this radiation can only contain information about these three quantities, about the black hole mass, its charge, and its spin. All right, this is a problem because it means now that information is lost in a black hole. So if you had some things fall into the black hole, you waited it for it to radiate, you gathered all the radiation and analyzed it, even to infinite precision, you couldn't reconstruct what fell into the black hole originally. So to make an analogy, you might want to compare this with the case, say, of throwing a dictionary into the fire. I don't recommend that you do this. It's a thought experiment. But you could suppose that you take a book and you throw it into the fire. The book is going to burn up. The fire is going to radiate. But what we know is that this process is actually totally reversible. No information is actually lost in this process. In other words, if you had an infinite number of detectors that could detect the radiation with infinite precision, you could actually reconstruct what it was that was burned in the fire. Or said another way, if you filmed this process and then ran the video backwards, the backwards video is entirely consistent with the laws of physics. You don't violate any physics in the movie where the book is going from radiation and then into the fire and then you pop out a dictionary. That's completely consistent with the laws of physics that we know. It's statistically very unlikely that that would ever happen, but there's nothing wrong with it physically. All right, on the other hand, if you did the exact same thing with a black hole, what Hawking's argument showed is that the process is not reversible. You could throw a dictionary into a black hole, wait for the black hole to evaporate, gather all of the information about the radiation, and the only thing that you would learn about is the mass, charge, and spin of the black hole. Said another way, there's no way to run this video backwards of this process and recover this dictionary. All right, so the question then of black hole information is whether or not information is really truly lost. Is quantum gravity telling us something? And this would be unique. So there's no other area of physics that we know where information is lost in this way. So this is what the paradox is asking us, is whether information is truly lost, or is there something that we don't understand about quantum gravity? All right, so just to touch on some proposed solutions. So we heard very briefly from Kara about the ADS-CFT correspondence. So this is a correspondence that, on the one hand, you have anti-de Sitter spacetime. So this is a spacetime of constant negative curvature that also has gravity in it. So you have black holes in ADS. You have, if you want, potentially a fully complete quantum theory of gravity. And the correspondence says that this is completely dual to a conformal field theory, where the conformal field theory is really, in some sense, just an ordinary quantum field theory with no gravity in it whatsoever. And the conformal field theory, we know, preserves information. So you don't have any kind of information problem in the conformal field theory just by virtue of it being a normal field theory with no gravity. But because of this duality, and because there are black holes on the other side of this duality, you can use it to argue, and for some people this was sort of the most convincing argument, that information should not be lost in the black hole. Because if on this side of this duality, you have this evaporating black hole, there's a perfectly unitary or a perfectly consistent description of the same process on the CFT side in which no information is lost. So even if you don't necessarily understand the details of how that information is being preserved, the fact that there is this duality where we know on one side no information is lost is compelling evidence that there should be no information lost on the other side. Yeah. Please, please.
Thanks. So maybe you could help me settle an argument I have with my chemistry teacher wife, who's not here right now.
I'm sure you're going to represent her accurately, though.
I'll reference you by name. She teaches her students that in all changes, in all experiments, entropy has to keep going up. You always have to lose information. You always have to tend towards chaos. Can I now rebut her by saying, actually, that's only true in black holes. 100% of what you're teaching your students only applies to black holes. Or, as she always points out, have I missed a giant point in the argument and I'm still wrong?
Yeah, good. So statistically speaking, what she's saying is correct. If you have a system and you sort of coarse grain it over large scales, you're always going from a system that has lower entropy to a system that has higher entropy. So you're always, in that sense, losing information. But you're losing information because when you look at a system like a gas, you're coarse graining. You're not keeping track of each individual location and each velocity of every particle in the gas. If you were to do this, no information would actually be lost. And so the statement that entropy is increasing and that processes are irreversible, in some sense is a statistical statement, or it's a statement about the likelihood of something happening. So again, it goes back, you could also, there's this famous example of like, you can't unscramble an egg. Physically speaking, you can. But what it means is that like, all of the heat and all of the little eggshells would have to be aligned to incredible precision so that when you let them go, they all came together and the radiation came in the right way, that out pops an unscrambled egg. So that process doesn't actually violate any laws of physics. It's just so unfathomably unlikely that that would ever happen. So when we talk about information being lost in that sense, it is because we're sort of coarse graining over macroscopic states. But if you actually kept track of everything to infinite precision, no information is truly being lost. Does that make sense?
You're saying that the rule book says it's possible, it's just we shouldn't live our lives as if it's ever going to happen.
Yes, that's yeah, that's right. Yeah.
So I've heard things like this before, and just a gap in my understanding, I think, is, we're basically positing a conservation law for information. But how do you quantify information? In the context of comp sci, I go, sure, you have bits or something. But in the context of a physical system, I have a subjective idea of what it means to have information about a system.
Yeah.
But if you're talking about creating or destroying it in a mathematical sense, I don't understand what the mathematical definition would be.
Good. So mathematically, what I'm talking about is that all of the processes should be unitary. So if I have some initial state and some final state, I can relate these two processes by a unitary operator. And what that unitary operator means effectively is that it's always a reversible process. This is also related to the statement that probabilities should always sum to 1 in a theory. That if I look at some initial state, if I add up the probability over all of my possible final states, the total probability that I end up in some final state should always be 1. And so these are all ways that's mathematically one way of framing what we mean by information being conserved in this sense. Now there's people who study black hole information have much more refined notions of information than that. But strictly speaking, what we're talking about here is a loss of unitarity. All right, so some people considered this to be sufficient evidence that the problem was solved, that even though we didn't really understand the specific details of what was going on the gravity side of things, nevertheless, we knew that information had to be conserved because of this duality. But you could raise some objections. One objection that you might raise is that we actually don't live in anti-de Sitter space-time. And it's possible that there are theories of quantum gravity that exist in anti-de Sitter space-time that don't exist in our space-time, that are actually de Sitter. So I should say, so anti-de Sitter space-time, this is this space-time of constant negative curvature. It turns out, and we'll say more about this, although I think I'm kind of running out of time, a little bit, is we actually live in a space-time of constant positive curvature. And anybody who's ever said that it's easy to go from one of these spacetimes to the other by just flipping the sign of the cosmological constant doesn't know what they're talking about and is totally lying. And any result that's proved in anti-de Sitter spacetime, it always seems to be infinitely harder to prove an analogous result in de Sitter spacetime. So just because this is true for anti-de Sitter, you shouldn't necessarily trust that it's going to be true for our universe. I would point out to you another caveat, is that the ADS-CFT correspondence at the end of the day is it does have the status of a conjecture. It's not proven. And it's possible that this correspondence, this duality, fails precisely at the point where these issues such as quantum information in a black hole become important. I think this is, not many people believe this, but I think at least for me, it's an important caveat in this argument. There's been recent development in thinking about these issues. So there's been some very cool work in trying to understand exactly how information might be conserved in a black hole. It involves basically, so Grant talked this morning about this path integral approach to quantum field theory, where you sum over all possible paths of a particle. In quantum gravity, it turns out that the path integral you're doing can involve sums over space-time geometries. And what these people showed is that if you actually summed over the right space-time geometries, you might be able to explain basically what's the right way of saying it? Why information in a black hole actually does escape in the way that we think it might. I should say also, though, that the caveats with both of these explanations is that neither of them give us any indication of what's going wrong with Hawking's original calculation. So Hawking's original calculation was done in this regime of semi-classical gravity. Neither of these explanations would tell you specifically why you can't do that calculation, why there's a problem with that calculation. So even if these answers turn out to be correct, there's still something that we don't understand about quantum gravity in this semi-classical limit. And I should say, too, that I think in all of these cases, it's believed that if information is preserved in black hole evaporation, that it necessarily involves some kind of non-locality, which again is something that we're very not comfortable with in usual physics. But there's going to be some sort of revolution in how we understand fundamental physics is working. And I should say some non-locality over very large distances. Okay. All right. The third problem that also lies at the interface of particle physics and gravity is a cosmological constant problem. So just to give a very brief history of the history of the universe. So in the 1920s, people largely believed that the universe was static, that it looked more or less the same for all time. It was homogeneous. It didn't have a beginning. It didn't have an end. In 1929, Edwin Hubble looked at not on a first name basis. Edwin Hubble looked at very distant objects, and he discovered that in fact, objects that were far away from us were moving away from us with a velocity that was proportional to their distance. So here D is the distance, V is the velocity, and they were moving away from us at a velocity proportional to this distance here, with h naught being this proportionality constant. So this was a big revolution. It completely threw out this notion of the static universe. And it implied then that you could have a universe that had a beginning or had an end. Because if you have a universe where everything's moving away and you run the video backwards, at a certain point that means that everything would have originated more or less at the same point. All right. In 1998, things kind of blew up again when people measured that not only are distant objects moving away from us and therefore the universe is expanding, but that this expansion rate is accelerating. So this should be slightly mind-blowing because we believe that at the largest distances, gravity is the dominant force. And gravity is always an attractive force. You never have repulsive gravity. And so if things are moving away from each other at a faster and faster rate, it means that there has to be something else responsible for this. There has to be some other force that's pushing everything away from each other. All right. All right. Now, it turns out that this accelerating expansion can be accommodated, I should say, by Einstein's equations. And it can be accommodated by simply adding this extra term to Einstein's equations that go by the name of a cosmological constant. And in fact, this cosmological constant wasn't introduced for the first time in 1998. It was introduced originally by Einstein to accommodate this picture of the static universe. So remember again, gravity is the dominant force at large distances. What that means is that if I have a whole bunch of galaxies that are attracting each other, the universe shouldn't be static. It should be collapsing in on itself. And so Einstein had introduced this constant into his equations, basically to stop the universe from collapsing inward on itself. And then once Edwin Hubble discovered that in fact the universe wasn't static, that it was expanding, Einstein threw away this constant and famously called this the greatest blunder of his life. But now, with the discovery of the accelerated expansion, we need to reintroduce this cosmological constant piece back into the equation to explain this accelerated expansion. So just some properties associated with it. You can think of this as being like a uniform energy density associated with empty space. It doesn't dilute as the universe expands. Grant mentioned earlier the zero-point energy of a harmonic oscillator. We're going to come back to this, but it's related to the zero-point energy of a harmonic oscillator. And what's interesting about this is that in every other field of physics, the only thing that ever matters are energy differences. You never care about the absolute energy of anything, right? So you can always, if you have some potential, you can always scale it up or down by a constant. And the only thing that matters, say, is the relative potential between 2 points. Or if you have some transition in an atom, the only thing that matters is the difference in energy between those energy levels. Gravity is the exception to this, where the absolute value of the energy matters because energy gravitates. And so in other cases, you're free to throw away 0-point energy. In the case of gravity, you can't throw away 0-point energy anymore. This is a source of gravity. And this also goes by the name of the vacuum energy, this cosmological constant. Also to put in some perspective, so we have many complementary ways of measuring now the energy budget of the universe. We know that 5% of the energy budget of the universe is made up of observable matter. We heard that excellent talk this morning about how 25% of the energy budget of the universe is made up of dark matter. The energy associated with this cosmological constant is responsible for 70% of the energy budget of the universe. So this is a non-trivial contribution to our understanding of what comprises our universe today. Okay. This is a mathematical explanation for the accelerated expansion. What is the physical explanation? So what is the physics behind sticking this cosmological constant here? So as we mentioned, 0-point energy can be a source of this vacuum energy. So fortunately, you're all experts in quantum field theory now, so I can go through this very quickly. But here we can consider a free scalar field. So this is some field phi that takes on values times t and position x. I'm going to be interested in the Fourier transform of this field here. So instead of phi and t and x, I can think of phi as a function of t and its momenta p. If I plug this expression into the equations of motion for my free field, what I get is an equation that looks like this. And you should hopefully recognize this as the equation for a harmonic oscillator for each value of the momentum p. So basically what this is saying, and Grant also discussed this earlier, is that a quantum field you can think of as an infinite number of harmonic oscillators. In this case, it's an infinite number of harmonic oscillators, each with one energy p. And as Grant also discussed, in fact, I think we saw it on more than one slide today, we know that the quantum harmonic oscillator has a ground state energy that's non-zero. So if my oscillator is even in its lowest state, there should be some energy associated with that state. And the way to get the energy density for a free field in its ground state is to sum up all of the 0-point energies for all of these harmonic oscillators, so one at each p. So in other words, I take this ground state energy here. I've also set h bar equal to 1 in this expression here. Thank you, Nick. And this should be the total energy that's stored in my quantum field. And this is formally infinite. This diverges, and this is formally infinite. And this tells you that you would expect to have an infinite 0-point energy stored in a single field. All right, so fortunately, as we discussed before, you can say, hang on, I know that I actually can't trust my field theory, we said, at energies above m Planck. And so I can take the integral on the previous slide, and I can set a cutoff. I can stop integrating once I hit p equals m Planck, because I can say, oh, I have no idea what happens beyond that point. And you can calculate the energy density stored in a field that way. And then you can convert that energy density h into what the appropriate value of the cosmological constant lambda should be. So if you do that, and you then compare the theoretical prediction for the cosmological constant compared to the observed value, you find that you're off by 120 orders of magnitude. So this is called one of the worst predictions in theoretical physics, full stop. All right, so this is the cosmological constant problem. This has been around for a while. It is still an open problem. So there have been many possible proposed solutions. One is the idea that we live in a landscape of vacua. All of these have different possible values of the cosmological constant. And we have to live in one that's compatible with there being human life so that we can have this conference and ask this question. And that is what forces the cosmological constant to be small. Other things that people have tried to do is modify general relativity. So modify our theory of gravity to try and either make this cosmological constant not gravitate or anything else. I think it's safe to say that in most of these cases, You can use modified gravity to get late-time cosmic acceleration, but it's still a mystery why the original cosmological constant, the original vacuum energy, should be set equal to 0. There are other things that people have proposed, such as the fact that de Sitter spacetime is unstable. So good. Having a positive cosmological constant means that we live in a spacetime of constant positive curvature. This is referred to as de Sitter spacetime. People have posited that maybe de Sitter spacetime is unstable, so you start out with some large cosmological constant, but it actually bleeds out over time, kind of like the Schwinger effect. When you have very strong electric fields, you pair create, and the field kind of dissipates over time. Maybe you could say the same thing about a cosmological constant. And then the fact that there are 3 dots here are to indicate that there is an infinite a number of solutions that have been proposed to this problem, and no consensus on what the answer is. So one thing that I want to emphasize is that these are 3 truly distinct problems. So they all lie at this interface between gravity and particle physics, but they are not the same problem. So in other words, if someone tomorrow was able to prove that string theory was the correct UV completion of general relativity, this wouldn't at all help us answer the black hole information problem or the cosmological constant problem. So when people talk about the mystery of quantum gravity, what I want to impress upon you is that there are many mysteries in quantum gravity. There are many things that we fundamentally don't understand about this intersection between gravity and particle physics. Okay, so what's new? I don't know. Do I have time? Should I? Okay, very good. All right, so there's been sort of a resurgence in interest in the last few years. I think Grant talked about this as well, of trying to understand what is the allowed space of quantum field theories. And the way that we do this is we impose theoretical consistency conditions on our theories. And we try and understand, in the absence of data, under certain assumptions, what can we learn about our theory just based on mathematical consistency? So this is an old idea, but there's been a whole bunch of new tools developed in the last few years to help us try and understand this. And you might think that general relativity could be particularly amenable to this type of approach. I mean, for one reason, the fact that we're desperate because we can't actually probe these energy scales experimentally. We can only use conditions like theoretical consistency to learn about the UV completion of gravity. But secondly, remember that general relativity is the unique Lorentz invariant theory of a massless spin 2 particle. What that means is that already, in the absence of experiment, there are very strong constraints on what a theory of gravity could look like. And you might hope that those types of constraints persist at ultra-high energies. And so you might be able to extrapolate what the UV completion of gravity should be just based on theoretical physics alone. And I should emphasize that this is very much a particle physics approach. So again, we're completely abandoning the notion that general relativity has anything to do with gravity. And we're saying, let's treat this purely as a theory of particle physics. What can these new particle physics tools, so tools that are made to think about quantum field theories, tell us about the UV completion of gravity? So I should say that Grant is an expert on these things, so I'm going to defer any questions to him. But the basic idea is the following. So you assume things like Lorentz invariance, unitarity. So this, again, you can think of as a statement that probability should add to 1. We have formal notions of what causality should look like in our field theories. So these are things that we assume are true about our theories to arbitrarily high energies. Then what you do is you consider, this is a 2-to-2 scattering process. You've already seen this today as well. But basically, I'm imagining sending in 2 particles, something happens, and 2 particles come out. These 2 particles could be gravitons, but they don't have to be. I just assume that there's some gravitational physics happening in here. And then I can start asking questions like, what modifications of general relativity are allowed? So in other words, if I take general relativity and I add some new terms to it that I think might reflect this UV physics, this higher energy physics, can I constrain what those terms look like based on theoretical consistency conditions? And the answer to this question is yes. Another question that you might ask using these methods is how unique is string theory? So basically, can you use these tools to isolate string theory as the unique, again, weakly coupled UV completion of gravity? I think there's been a huge amount of progress, and I think there's growing consensus that the answer is going to be yes here as well. There are then more speculative questions that you can ask that it's not clear that the present tools that we have are up for the task, but nevertheless, we can ask them, such as, is the UV completion of gravity weakly coupled, or is it going to end up being something in a strongly coupled regime where we're going to have to develop new tools to understand this theory better? And finally, we can ask very specifically, what happens at energies above the Planck scale? So if I scatter particles in a regime where the energy is so high that I actually expect to form black holes, can I calculate that scattering process? What are the tools that I need in order to calculate that scattering process? Okay, so the punchline that I want you to take away, these problems are old, important, and very hard, and we need your students to help us. So how do we get them there? So I interpreted this question narcissistically and say, don't do what I did. So I was told as an undergraduate that it didn't matter what classes you took, that the point of liberal arts education was to be very broad, and then you could do whatever you wanted after that. So I took lots of classes called things like Ancient Utopias in Imaginary Places or Border Crossings in Mexican-American Literature, and then went to apply for graduate school, and it's kind of like, oh, crap. So I would definitely make it clear to students who are as dense as I was that it's really important to have a very strong foundation in math and physics as an undergrad. And with that said, don't make the error of the converse, which is I think there are a lot of students who come in and are very eager to take things like quantum field theory as soon as they can. And I would say that it's super important, especially as someone who reads graduate school applications, that students first really have mastered the basics and the breadth as well, and not just rush to the sexier, more advanced classes. I would also, and Grant emphasized this as well, I would say undergraduate research is essential. This is actually an area where I didn't screw up as an undergrad. So REUs were mentioned. I didn't get into any REUs, but I submitted my resume to Berkeley Labs. And a few months later, I got a call from a physicist who was working there, and we started a summer project together and then a longer collaboration. And so I definitely encourage your students to look at national labs as a potential place for doing summer research opportunities, especially if they don't get an REU or some other opportunity. But that was a very formative experience for me. And I would say undergrad research is essential, especially in experiment, even if they want to go on as a theorist. So I would say that, and Grant mentioned this as well, it's really hard to do a problem as an undergrad in theoretical physics. It's much easier to find an experimentalist willing to take you. I would also argue it's better for your career. I would much rather have a theoretical physicist who understands something about experimental physics than somebody who's never been exposed to that before. So again, I definitely encourage, even if you have students who are very interested in theory, encouraging them to do something experimental. And then my other big blunder as an undergrad was I believed that asking professors questions was a sign of weakness and you should never do it. That was clearly very wrong. So I definitely encourage you to encourage your students to be as interactive with their professors as possible. I love it when a student comes to my office hours asking questions about physics as opposed to questions about their grade or the exam or something like that. And they will certainly learn more and have a better experience. And then it's crucial that they do have letters of reference at the end of their undergrad career. So there really need to be people who know them well beyond, oh, this person got an A in my class or whatever. So I would definitely emphasize having students talk to faculty members. But that's all I wanted to say. Thank you so much. Sorry for going over.
Excellent. Any questions for Rachel?
Hi, thank you. I guess my question is maybe two parts. Number one is the assumption was a massless spin 2 graviton. Would that, in the standard model, necessitate that there are other particles that are maybe spin 2 or spin 3 halves or something? And I guess the second part of the question is, are there other masses that would work?
Yeah, that's a really good question. So there's nothing wrong with just adding a single massless spin 2 particle to the standard model of particle physics. If you want to add more spin 2 particles than that, it's actually interesting. You can show that it's not consistent to have more than one massless spin 2 particle, that if you want to start adding more spin 2 particles to your theory, they have to have a mass. So you could have a standard model of particle physics that has a massless spin 2 particle, but then also massive spin 2 particles. Now, there's no reason, theoretically to necessarily include these, but there's nothing inconsistent with that as well. And you asked about 3/2 as well. So this is a type of particle that you would actually get if you had supersymmetry. So if you take your standard model and you supersymmetrize it, you would have particles of spin 3/2 as well appearing. And we don't see low scale we don't see the superpartners, say, at the LHC, but it doesn't mean that they aren't there at higher energies.
Other questions?
Just clarification for that worst prediction of all physics of all time.
Yeah.
That observed cosmological constant, is that based off of the 98 data then of the dark energy acceleration?
Yeah, but it's been refined since then, but the value itself hasn't changed that much since 1998. Yeah.
Thank you.
So there is massless particles and there's positive mass particles. We don't have the notion of a negative mass.
No, in general, these are considered inconsistent. So an important feature, and this also goes in the direction of having a unitary theory, is that the energy of your theory be bounded. And if you have massless particles, it actually means that you have instabilities in your theory. And so it's you can't have particles with negative mass in a stable theory, is maybe one way to say it. Yeah. So, sorry, can I put a caveat to that? Yeah. So the Higgs, in some sense, is actually a caveat to that. So formally, you write down a mass term that has the wrong sign, but we know that it's rescued by the rest of the potential curving upward, and that negative mass point is not actually like the state that your particle ends up living in. So all of the physical particles do have positive masses, but when you write your theory down, you're actually writing down a theory of something that looks like it has a negative mass. So it's not totally, we do take advantage of negative masses.
You mentioned a shift in understanding in locality to understand the information paradox. I'm wondering if that at all relates to the shift in understanding of locality when it comes to entanglement.
Yeah, very much so. Oh man, I hope nobody who's actually an expert on this is listening. But basically, one of the ways that these what's the right way to say it? So one of the ways that you can think about resolving the black hole information paradox is to think carefully about what information outside the black hole is entangled with what information is inside the black hole. And what people have found is that I want to deflect this to it. So I'm not going to answer it correctly, and so I want to deflect, but it's a very good question, and those two things are very closely related to each other. Yeah.
You had mentioned that the options for the particles were limited by Weinberg no-go. Could you just elaborate on that just a little bit? Because I don't know anything about that.
Oh, yeah, very good. So basically, Weinberg was using the tools of quantum field theory and sort of imagining a hypothetical process where you send in massless high spin particles and looking at the possible amplitudes, the scattering amplitudes for things that you could get out. And what he could show this way, so what's the right way to say this? So good. The methodology that he's using, if you use it on, say, a spin 1 particle, what you conclude is that charge has to be conserved. So these are some constraints looking at the scattering of a spin 1 particle. You look at what comes out the other side, and this constraint tells you that charge has to be conserved. If you do the same, if you run the same argument with massless spin 2 particles, what you get out on the other side is actually the equivalence principle. So Weinberg can derive from field theoretic considerations when you look at scattering of massless spin 2 particles that the equivalence principle must be obeyed. When you run the same argument with massless higher spin particles, what you basically find is that you can't have any interactions. So the interactions in some sense become over-constrained at that point so that they're not even allowed. So for low spin particles, you have arguments that put constraints on sort of how the interactions can work. And then once you get to higher spins, there are too many constraints to solve, and that you can't find an interacting theory that satisfies them. It's a little hand wavy.
Last chance for questions. All right, let's thank Rachel one more time.
Thank you.